Hi, my name is Anuj Bhatia, and this is my lab report for Lab 4 oscillations. So the main purpose of this lab is to analyze the motion of a mass attached to a spring swinging in an arc while the mass also oscillates on the spring. And we will use Tracker to acquire data for the spring mass system and also create a computational model of the system in GlowScript to compare. And some fundamental principles I used for this lab were the energy principle and Newton's second law. And at the end, we concluded that the spring mass system did indeed satisfy the energy principle based on our results. So some of the main physics ideas and principles I used for this lab were that kinetic energy is equal to 1/2 mv squared, gravitational potential energy is equal to mg times change in y, which is the height, spring potential energy is 1/2 ks squared, where s is the compression, velocity update is vf is equal to vi plus f net over m times change in t, and position update is rf is equal to ri plus v times change in t. So some initial conditions for my experiment were that the system was the mass on the end of the spring, the surroundings for the spring and the earth, because these are the forces that we considered when analyzing in the computational model. And then the ball, initial mass of the ball was 0.402. The spring constant was 6.83 Newton meters. The relaxed length of the spring was 0.123 meters. Initial position was negative 0.110, comma 0.642, comma 0 meters. Initial velocity was 0, and change in time was 1 over 210 seconds. So some details about the actual experiment or tracker can be seen in this image, and it shows the track positions of the mass oscillating and swinging in an arc, and then graphs for the x and y positions of the ball can be seen on the right, and the ball can be seen moving in an oscillating pattern in both graphs, and then we'll later use these graphs to compare the data generated from the computational model. So some details about the coding or the computational model. So this is the first chunk of code, and it sets some of the initial conditions for the model, like mass, position, and velocity. And then it also reads and imports the data from the tracker CSV. And then lastly, it sets the delta t as 1 over 210 to update the model for each iteration. So for the next chunk of code, this chunk of code sets the values for some constants, such as gravity, spring constant, and the initial length of the spring, and then it sets the value for L, the L vector, and the spring compression, or S, and then lastly defines kinetic energy, gravitational potential energy, spring potential energy, and total energy. So this next chunk stores the values of each of the initial energies for each iteration. It initializes gravitational and the spring force values. It updates the ball's position and velocity for each iteration. It prints the spring's position at certain times, and then it updates the L vector and spring compression for each iteration. And lastly, this last chunk of code calculates the new energy values and changes in all energies. It sets the colors for graphs to plot each energy value. It plots and compares the data from the real tracker CSV data, and then it updates time by change in t for the next iteration. So now we can compare the data. So the red line is the data from the actual tracker CSV or the experiment, and then the blue line is the data from the computational model. So as it can be seen from the GlowScript simulation, there are some slight differences between the experiment and the computational model data. So the x position versus time graph is actually very similar, but the period of oscillation for the experiment in the y position versus time graph is much smaller for the actual tracker model. And some possible sources of error for why they're different could be the spring being treated as massless in our computational model when in real life it has mass, and the surrounding forces such as air resistance being ignored because we only considered gravity and the spring, or earth and the spring, as the surroundings for the computational model, and then obviously some possible errors in measurement or of values from the tracker data could be an error. So for my additional questions, the first additional question is, for your model system, is the energy principle satisfied? And justify your answer by discussing briefly your plots of energy changes. So yes, the energy principle is satisfied in my model system. This is because only conservative forces act on the system, which are the spring force and the gravity force, and no other external forces act on the system, or at least ones that we consider. So the change in energy must be zero, and this can be seen in the graph below, which shows that the initial energy equals the final energy from the computational model and the experiment. And then for the next additional question and the last one, so using the data you obtain in Tracker, make two separate estimates of the oscillation periods, one in X and Y, and then compare the two estimates. So using the Tracker data, the average time from peak to peak was 1.69 seconds, and the average time from trough to trough was 1.67 seconds for X positions. And averaging these two period estimates to given a good estimate for the period using x values, which is 1.68 seconds. And then doing the same thing for the y values, we got an average period of 1.51 seconds. So estimates are different because the mass oscillates and swings at an angle. So its period is made up of both x and y components in reality. And another possible source of error for why they're different could be that the time increments were too big or too small to properly capture accurate times for peaks and troughs. But that's my lab report, and thank you.